All right, and our next speaker is Alexia Kirby from the University of Ottawa, and she'll be talking to us about her work in mapping concussion for early diagnosis by molecular MRI.
Good morning, everyone. Thank you all for coming. Okay, great. Thank you. Concussion is a type of traumatic brain injury that causes complex neurological impairment, but is invisible to standard imaging. We used to think of concussion as a blow hard enough to the head or the body where the brain would shake back and forth and cause some sort of surface bruising, but we now know that it's actually the rotational acceleration and deceleration that causes stretching and shearing of the axons, and that leads to this so-called neurometabolic cascade of concussion. Despite all of these biochemical events that are going on and all of these symptoms, concussion still remains difficult to diagnose. So difficult, in fact, that up to 90% of patients with mild traumatic brain injury or concussion go unidentified and undiagnosed in the emergency department. 25% of teens in the US have already admitted to having a concussion. Up to 3.8 million sports-related concussions occur in the United States alone each year, and over 40% of concussion patients return to their activities too early, leaving them susceptible to further injury. So if you go to the hospital for a suspected concussion, they might walk you through some sort of testing like this. So there's the Glasgow Coma Scale to assess your level of consciousness, the symptom evaluation checklist, some sort of cognitive screening. Do you know where you are? Do you know what day it is? And then repeat some sort of task back to them. This is the standard testing. However, at the bottom, there's a big red box that says this actually can't be used to diagnose concussion alone. So we have this problem where a patient presents with a concussion. All these damaging cellular responses are occurring in the brain. We can try to go through some subjective tools, maybe rule out other injuries, and then maybe get a diagnosis of exclusion. So this leads us to needing a diagnostic imaging tool for concussion. So that's what we developed. We chose to use aldehydes as a biomarker for injury for concussion. So we think these aldehydes are coming from two major pathways. First, there's a disruption of polyamine homeostasis, and that leads to polyamine catabolism and lipid peroxidation, so oxidative damage. And both of these pathways result in these aldehyde byproducts. So we developed PHBA as a CEST-MRI agent for concussion. It's this small probe that binds to aldehydes in vivo, and it creates a turn-on signal with CEST-MRI. And then I had to develop a model of concussion. So the old school method of doing this is a weight drop model where you hold a weight over a mouse's head and let go and hope that it hits the right spot at the right speed. I wanted something a little bit more sophisticated and something more translatable to, let's say, a football concussion. So I developed an awake, closed head mouse model of concussion where I could do reproducible impacts at these parameters. In order to continue on with this model, I needed to validate two things. One, that the blood-brain barrier permeability wasn't being disturbed, and that there was a behavioral phenotype. So I just checked the blood-brain barrier permeability with a DCE MRI, and all was good. There was no blood-brain barrier leakage. And then I developed all these behavioral tests to see whether or not my mice had a concussion, and it gave me the ability to score the concussion as well. So along the top, I have 5 pass or fail tests, and this gave me my neurological severity score, so a score of 0 to 5, 5 being the worst. And then I put the mice on some grids and filmed them for 3 minutes and counted how many footsteps they took and how many times their feet went through the grid, and then the percentage of time they spent walking around. So this is a healthy mouse.
Recording in progress.
You can see it's having no issues walking across the grid. And then this is an impacted mouse. You can see he's falling through quite a bit. So then I wanted to see whether I could see some sort of difference between mice with aldehyde dehydrogenase deficiency. So ALDH2 is responsible for getting rid of these aldehydes via oxidation, and I wanted to see if there was a difference between young and old mice. In terms of my experimental design, I would get a pre-impact mouse, do an MRI with our PHBA, and do my behavioral testing. Then I would impact the mouse, and then immediately post-impact, this is when you would do like your sideline concussion behavioral testing. Immediately post-impact, I would do just my behavior scoring, and then at 2 and 7 days, I would do my MRI again. In terms of my behavioral results, here I have the neurological severity score, again 5 being the worst. The black is the pre-impact, red is post-impact, and you can see overwhelmingly that there's an increase in the behavioral phenotype. And then these are the grid walk results, again an increase in the difficulties walking on the grid in all cases. I just wanted to point out that the wild type mice did not have a significant increase in their behavioral severity. So these are the imaging results. I'm super excited about these. So this is showing just a representative mouse from each of my cohorts. On the left, we have the naive pre-impact mouse. So this is their baseline level of aldehydes in the brain. And then in the middle, this is 2 days post-injury, and then 7 days post-injury. And I'm showing you the CEST map normalized to the pre-contrast image. So, as you all can see, the 2 days post-impact has a pretty big signal. And this is across the board. So on the right, I just quantified these mice on the left here, but you can see that there was some baseline level of aldehydes, it increased at day 2, and then it was back to baseline at day 7. So we found when the aldehydes are being produced. And then if we look at just the day 2 signal, here, this is all my different variables that I wanted to look at, the aldehyde dehydrogenase genotype and the old versus young mice. And there was actually a difference between all of the groups. So here, if we break down just all of my young mice and all of my old mice, you can see that the old mice had a increased signal, increased aldehyde signal after injury compared to the young mice. And then if we look here between my wild type and my 2 aldehyde dehydrogenase deficient mice, we can see that the wild type actually had less signal on day 2. And I'm just going to bring back this graph that I pointed out because there is a correlation we can draw here. So there was not a significant behavioral phenotype in the wild type group, and there was also less aldehyde signal compared to the aldehyde dehydrogenase deficient mice. So then I wanted to kind of zoom in and see what was happening on the cellular level. I wanted to verify that these aldehydes were being produced after impact on the cellular level. So aldehydes are pretty tricky to see. The only way that we can do it so far is to image them fluorescently in live cells. So I created this corticomimetic scaffold. So it had this outer, we called it the outer donut. This was made of a higher concentration of collagen and crosslinker just to give it some support. And then on the inside, we had this little collagen neural plug, so no crosslinker and a little bit less collagen. Together, it was my corticomimetic scaffold. This is my 3D brain in a dish. And then I was able to impact it with the same impactor I used on my mice. And then I used confocal microscopy to look at the aldehyde signal with a fluorescent probe that we developed in the lab previously. So here I just wanted to match the mechanical properties to an actual punch of a mouse cortex, and we did just that. And then here is the impactor tip over my little 3D brain here. This is the aldehyde signal pre-impact. It's hard to see on purpose. There's a really low baseline level of aldehydes. And then this is post-impact. So there was a big increase in aldehydic load after impact in live mouse neurons. So in conclusion, we've developed the first objective diagnostic tool for concussion, and it uses aldehydes as a biomarker. These aldehydes may be early propagators of disease, especially for individuals with aldehyde dehydrogenase deficiency. There are 500 million people worldwide with aldehyde dehydrogenase deficiency, so this is pretty relevant. The 3D brain in a dish confirms aldehyde production post-concussion in cells, and all of these together lead to potential avenues for personalized concussion diagnosis, therapy monitoring, and improved patient outcomes. Thank you to everybody that helped me out, and thank you guys for listening.
Wow, thank you for that great talk. This paper is now open for discussion. I'm going to start because I'm very greedy and I have so many questions for you. I'm really, really intrigued by the brain in the dish, as I'm not very familiar with that technology, and I wonder if you think of combining this with your 2 and 7 day MR CEST of the recovery period. And have you thought about that, or taking more time points in between those days?
Definitely, that's a next step. Yeah.
Very cool.
Yeah, we this is very new. We just kind of figured this out recently, but we're going to run with this little brain in a dish. Yeah.
Awesome, awesome. We have some more questions in the audience. You have the microphone, please go ahead.
Yeah, I think I'll be greedy next. Thank you. No, great talk. So if I saw your data correctly, you had pretty significant signal at day 2.
Yeah.
And then it diminished by day 7. Is that correct?
Yes.
So I'm just curious if you have, whether it's predictive or definitive, do you have any data to help inform on recovery from concussion rather than the initial diagnosis?
So could we use this probe to look at recovery pathways?
Yeah.
So there are statistics showing that a diagnosis leads to improved patient outcomes just based on their the doctor's orders. But I think probably if we see an increased signal, I think the higher the signal, probably the worse off the concussion is going to be. I also think that we can use this to look at whole body instead of just the brain as well, and that'll also dictate probably the level of injury and how long the recovery period will be. Yeah, but definitely something we're going to look at.
Yeah, that'd be tremendous if
Yeah.
it does. Yeah. All right. Thank you.
Thanks.
So along those lines, I guess, is the implication that on day 7, if there's no aldehyde signal, could that mouse play football? That's what we want to know.
Yes, exactly.
If it's a true biomarker.
I am not a doctor.
Right.
Thank you.
I think the whole point here that we have to keep in mind is that aldehydes are a very early signal in the pathogenesis of the injury. So just because the aldehydes are gone, they may have bound to DNA and proteins and created these adducts, and those create a cascade of events that are happening. So there are probably other serious things that are happening at day 7, but it's no longer aldehydes. Those are the
So
early
maybe
response.
you need a different biomarker. Yeah. For the
later
late stage.
response,
Sure.
yeah.
Yeah, I don't know. What is the typical recovery time for a concussion? I have no idea.
They want you to basically not do anything other than get up and walk to the kitchen for 2 weeks.
Okay.
Yeah. If you're diagnosed. So the whole thing is that a football player is probably just going to shake it off and keep going, and that's the danger.
Yeah.
One more question.
I have 2 quick questions. So the first one is, have you tested on different severity of MTBI? The second question is that the aldehyde signal quite homogeneous over the whole brain, or do you see local hotspot?
So for your second question, so far it looks pretty homogeneous. We're only able to look at one slice of the brain right now just because of the CEST-MRI. We'd like to look at the whole brain and then see if where we impact the brain, if it creates an area of increased aldehyde signal. So if I hit from the side, are the 2 sides going to light up more than the middle? That's definitely something we want to look at. And I don't remember your first question. The stability of?
Severity.
Oh, severity. Also something I haven't really looked at yet. So I had to find the impact parameters that I could get a behavioral outcomes. So I'm actually giving the mouse a concussion and back off a little bit when it was too hard and we're at the level of traumatic brain injury.
Thank you so much.
Thank you.
All right, let's thank our speaker again.